Okay, determine the dead weight of a 1 meter long segment of the reinforced concrete box beam. Concrete is approximately 16 kilonewtons per cubic meter. A kilonewton is about 225 pounds, and a meter is about 3.3 feet. So as you can see here, I've drawn the cross-section of the concrete beam. So we're looking along the longitudinal axis. The first thing I want to do is calculate this cross-sectional area. Okay, so go ahead and calculate the cross-sectional area. That's what I did here. It's the outside area, which is what I'm tracing with a pen here. Outside area, that's the 0.7 times 0.62. But then I have to subtract off the cross-sectional area of the hole that's in the beam. So this is the hole. I have to calculate that area. As you can see here, that's 0.7, which is the outside width, minus 2 times the wall thickness, 0.11. These are all in meters, you'll notice. So this right here, 0.7 minus 2 times 0.11, that's this length along here. And then multiply that by the height of the hole. That's the 0.62, which is the outside height, minus 2 times the wall thickness, or I should say the thickness of the top and the bottom portions of this, the 140 millimeters, that's 0.14 meters. So this is the outside area minus the area of the hole, or the inside area. So the cross-section of the concrete, which is what I've shaded in blue here, that's 0.2708 square meters. So now I get to calculate what the weight of the dead load is. What it will be is this cross-sectional area, which I just calculated, times the depth. The depth of this is 1,000 millimeters. So from here to here, okay, that depth in and out of the paper is 1 meter, because he's asking about a 1 meter long segment. So you can put right there, 1 meter. Okay, so to calculate the dead load, of this section, I'll multiply the cross-sectional area that I just calculated by the depth by the unit weight of concrete. Okay, so we usually use W to represent a distributed load. DL, the subscript DL, means dead load. In this case, it means the dead load of the concrete beam along its length. So that'll be the cross-sectional area that I just calculated, times the depth, 1 meter in and out of the page, times the unit weight of concrete, 16 kilonewtons per cubic meter. When I multiply the cross-sectional area by the depth by the unit weight, I get 4.3328 kilonewtons. And again, a kilonewton is about 225 pounds, so you can do the math if you want to know what that is in terms of pounds. So I could present this as my answer. Or since this is in terms of meter of length along the beam, I could also say 4.3328, and then I could say kilonewtons per meter, meaning that it acts along the length of the beam. So that's an example of how to calculate the self-weight of a beam, in this case a concrete box beam. Okay, another example of calculating dead load. So consider this. The roof system of a building consists of a 4-inch thick reinforced concrete slab resting on 4 steel beams. That's the cross-sectional area, 16.5 square inches. They are supported by 2 steel girders. A girder is like a big beam. There's 2 steel girders run along the sides. So we're looking at the floor plan of I shouldn't say the floor plan, but the roof plan of this building. So the 2 girders along the sides, these are the beams. The slab is drawn on top. The slab would cover the entire roof. This is a cutaway here, but the slab would actually cover the entire roof. Okay, so where was I? The cross-sectional area of each girder is 44 square inches. The girders are supported by 4 columns at A, B, C, and D. Pardon me, A, B, C. Let me try that again. A, B, G, and H. So those are where the columns are located at. calculate the dead load, DL is dead load, acting on girder AG. So I want to calculate the amount of dead load acting on this girder along here, which will of course be the self-weight of the girder, as well as the slab. The weight of the slab has to be carried by that girder, as well as the reactions from these beams that attach to the girder. So I'm going to I'm going to analyze CD. I'm going to draw beam CD and analyze what load that beam CD is carrying, and therefore I'll know what the reaction will be at point C that's feeding into girder AG. The analysis of CD will be very similar to the analysis of EF. So I'm going to analyze CD now. Okay, so the tributary area is the surface area that's feeding into a particular member. So if I want to analyze CD, okay, imagine if someone were to set their foot on this portion of the roof where you see the X there. The X is closer to beam CD than it is to EF. So that means that CD, we would assume, is carrying the weight of the person's foot that's acting on X. But if the person sets their foot over here, well, now they're closer to EF, so beam EF would probably carry that weight. And so the idea of a tributary area, how much of the area feeds into the beam that I'm analyzing. So if we go midway between C and E, midway between D and F, okay, I cut this area in half, the area between this beam and this beam, cut that in half. Similarly for between beam A, B, and CD, cut that in half, cut that area in half. So you see those two red lines there? This area right here, I'll shade it in red. That area that I shaded in red would be the tributary area for CD. So now I'm going to analyze that. So now I'll bring up the next drawing. Okay, that's what we're looking at here. Beam CD, CD, and its tributary area. So this right here. Okay, so notice I say here, step one, girder AG supports beam CD and beam EF. Those will be very similar analyses. So I say, therefore, consider CD. Consider CD. Due to symmetry, the analysis would be similar to the analysis of EF. It would be the same tributary area for beam EF. So I choose to analyze CD. Okay, so I say consider CD. Tilde means similar to EF. Actually, it would be identical, not just similar. So tributary area, what is that tributary area? We know that the building is 18 feet wide. Where does the 8 come from? From the original drawing, these beams are 8 feet apart. 8 feet apart, so midway between D and F, or C and E, that's 4 feet. 4 feet right there. And then between B and D, or A and C, 4 feet right there. So that's where the 8 feet is coming from. So the tributary area, 8 feet wide by 18 foot. Okay, you see that? So if I multiply 8 by 18, I'm getting 144. So 144 square feet would be the tributary area of CD, or EF for that matter. So now I want to calculate the weight of the slab. You see shaded here in kind of red and blue. That's the slab that's being carried by beam CD. I want to calculate the weight of that slab. Okay, weight of the slab, here it is. Unit weight of concrete, 150 pounds per cubic foot. You have to remember that number, unit weight of concrete, although it's probably found in tables of material weight. If you look in your material science textbook, unit weight of concrete times roof tributary area, which I just calculated, times 4/12 of a foot. It's a 4-inch thick slab, so that's 4/12 of a foot. So the entire weight of this portion of the slab, 7,200 pounds. I want to calculate that as a distributed load. So if I were to take a 1-foot segment of this, see that 1-foot strip? That's 1 foot. A 1-foot strip right there. What is this as a distributed load? Well, that's what I'm calculating here. Take the 7,200 pounds that I just found, divide that by 18 foot, or 18 feet, because that's the span between C and D. So divide that by 18, and I'm getting 400 pounds per foot. Okay, that's just the concrete. What about the self-weight of the steel beam? So just to put this number off to the side for a minute, I call that W sub C, C for concrete. Now I'm going to calculate the self-weight of the beam CD. So what's the weight of the beam itself? Weight of a steel beam? Actually, this is the steel beam that I'm analyzing, that is CD from the previous illustration. The cross-sectional area, 16.5 square inches. The length, that spans 18 feet. That's 216 inches. So now I calculate the volume of that beam. Remember this drawing? The volume of beam CD is what I'm looking for here. The cross-sectional area, 16.5 times the span, so A times L. I've got 3,564 cubic inches of steel that make up that beam. I want to convert that to cubic feet. So I take the 3,564 cubic inches, multiply by 1 foot for every 12 inches, and then cube it. This is sometimes called the factor label method if you've taken chemistry. Or I'm sure you've taken chemistry, you need it for this class, or you need it for your engineering curriculum. So cubic inches will cancel with cubic inches, leaving me with cubic feet. So I've got 2.0625 cubic feet of steel. Then the total weight, pay no attention to this, I made a typo there. So total weight, unit weight of steel, 490 pounds per cubic foot. Look that up in your materials science textbook. Unit weight of steel, 490, times the volume of steel that I just calculated. So the total weight of that beam, 1,010.625 pounds. And then I want to convert that to a distributed load. Remember this drawing? That's the total weight of beam CD. The total weight is the 1,010 pounds. That's the total weight of beam CD. I take a little strip of that. See that right there? A 1-foot strip. I want to know what the weight of that 1 foot portion is. So as a distributed load, take the total weight, 1,010 pounds, divide by the 18-foot span, 56.14583. The 3 repeats. That's pounds per cubic foot. So I'll call that W sub S, subscript S for steel. Okay, so remember that number. So the total dead load acting on beam CD, the total dead load is the weight of the concrete slab, 400 pounds per foot. I need to add to that the self-weight, about 56 pounds per foot. Okay, so I'm going to draw a picture that would be similar to what you used to see in statics, a picture of the beam, a free body diagram of that beam CD, where I have a distributed load that is the combination of the concrete and the steel weight. Okay, and here it is. We're looking at the beam from the side. Point C, point D. Okay, we're looking at it from the side. I calculated the weight of the concrete, calculated the weight of the steel. Add those together. Concrete, 400 pounds per foot. Steel, 56.15 pounds per foot. That gives me a distributed load of approximately 456.15 pounds per foot. So that's what you see here, the distributed load. So then you can use what you learned in statics. What you learned in statics is how to calculate the reactions. the reaction at C and D, so I'm assuming that beam CD is simply supported, pinned at one end and roller at the other end. So I say from statics, the reaction at C is equal to the reaction of D, because this is a uniformly distributed load. It's symmetric, 4,105.31 pounds. So those are the reactions at C and D. So that's it for my analysis of beam CD. Let me go back to the original drawing. The reaction at C, can you see this? Acting down. The reaction at D, acting down, is the 4,105 pounds. And well, I'm showing the arrows pointing up because that is the reaction from the girder on the beam. So beam on the girder will be 4,105 pounds at each end, but girder on beam, that's up. So if I look at this roof plan, 4,105 pounds going down, 4,105 pounds going down. Similarly with EF, 4,105, 4,105. So now I have to do a similar analysis for beam AB, and it'll be the same as the analysis for GH. So I've done the analysis for this beam and this beam. Now I need to do the analysis for AB and GH. I only need to do one of them, AB. Okay, step 2. Girder AG also supports beams AB and GH, so analyze AB. GH would be the same analysis. Let me go back to my original roof plan. Okay, look at AB here. The tributary area will only be this portion here that I'm outlining in green. The width of this tributary area would be halfway the distance between B and D, or between A and C, so I didn't draw this perfectly, but it'd be halfway between, so maybe more like this. So see this area that I'm shading in green? That area that I'm shading in green is the tributary area for AB. It'd be the same area for GH, the same size. Tributary area for GH. Do you see that? So how wide is it? This is 8 feet from B to D, so 4 feet along there, 18 feet long. Okay. So that's what I've drawn here. The tributary area, 4 feet wide, 18-foot span. Calculate that tributary area, it's 72 square feet. So what is the weight? The weight of this slab. Okay, so here I am calculating it. Unit weight of concrete times tributary area times slab thickness is 3,600 pounds. That's the weight of this portion of the concrete slab. I turn that into a distributed load, W sub C. If I were to take a 1-foot strip, see that strip there? It's 1 foot. Okay, so take the weight that I just calculated, 3,600, divide that by 18. It's 200 pounds per foot, half of the W sub C that I calculated for the beam CD. So let me call this W sub C. Well, I already did. I'll put a circle around it. Okay, now I need the weight of beam AB, the weight of the steel beam. It's the same steel beam that CD was, so it'll actually be the same weight, the same distributed weight, or the distributed load that I calculated previously. So now analyze beam AB. The weight of the beam itself, same as before, about 56 pounds per foot. It's the same size beam, so I don't have to do that analysis over again. Okay, so beam AB. We're looking at it from the side, 18-foot span. So the weight of the concrete plus the weight of the steel, 200 pounds per foot. That's what I calculated a moment ago. That's the weight of the portion of the slab that's supported by AB as a distributed load, plus the weight of the steel beam per unit length. That gives me a total of 256.15 pounds per foot. So that's what I've shown here. 256.15 pounds per foot. From statics, you can calculate the reactions at A and B, about 2,305 pounds. So that'd be the reaction at A acting down, the reaction at B acting down. The reaction on the girder acting back would be up, of course. So now I have all the information that I need to analyze girder AG. So let me bring that illustration back. So I was to calculate the dead load acting on girder AG. I calculated the reaction at A. Okay, I just did that. Calculated the reaction at G. It'll be the same as it was for A. I calculated the reaction at C, which will be the same as the reaction at E. So I'm going to draw a free body diagram of girder AG with reactions at A, C, E, and G. Okay, I know what the reaction at C is, same as E. I know what the reaction at A is, it's the same as G. And then I have to throw in the self-weight of the girder itself, so that will be step 3. Okay, so now step 3, analyze girder AG, which was originally asked for. Okay, I know the reactions at A and G. I know the reactions at C and E. You see, I calculated them. All of these have been calculated. The distributed load you see there, that's the weight of the girder itself. Okay, so in the directions it told you 44 square inches. This is for converting to square feet. Okay, remember the factor label method? How are the units going to work out? Square inches cancels with square inches. So I'll have square feet times feet. That's 24 foot length. Square feet times feet is cubic feet. So that's cubic feet, that's cubic feet. So those will cancel according to the factor label method. So that'll leave me with pounds. So that's the weight of the girder itself. What is that in terms of unit length? Okay, so 3,593 pounds divided by 24 feet, about 150 pounds per foot. Okay, so that is the W that you see here, distributed load 149.7 pounds per foot. Okay, so that is my analysis of girder AG, so it would be up to you as the engineer to determine if the girder is suited to take this amount of load. So girder AG, I calculated the 4 reactions using the idea of tributary area. I calculated the distributed load, which is the weight of the girder itself. The distributed load here would not need to account for the weight of the concrete slab because that's already been accounted for when I calculated these reactions. So I wouldn't have to calculate the weight of the slab again. That would be double dipping. Okay, so that's my analysis of the girder. Now if you wanted to design the column at A, remember the original sketch. Okay, here's the original roof plan. I could calculate what the reaction at A is and design the column A accordingly. There's a column at A, column at G. If I wanted to, I could find the reaction at A, which would assist me in terms of calculating the axial force on that column. So that is my discussion on dead load.